Hi, my name is Bhanu. Today I'm going to talk about creating a personal code search engine. This will be useful for small teams and also for individual developers. Developers looking for a relevant code snippet to solve this specific problem is an interesting topic for me personally. Why, sir? Developers of different experience levels have different ways to solve their problem. Someone with a healthy experience of, let's say, 10 years and above are more likely to solve a problem quickly. Let's consider a scenario of, let's say, someone wants to cache an endpoint, right? How do you cache your let's say static files or maybe data files or some endpoint? Someone with a decent experience, let's say 10 years and above, are likely to figure out a solution fairly quickly without any external help. Developers who belong to a second group, who have, let's say, an experience of 5 years and above, are likely to rely on some online results, probably also look through their old repositories and stick together a solution, probably longer than what the earlier group did. The third group, where you have developers who are fresh or probably have experience up to, let's say, 3 or 4 years, are likely to stumble upon a solution after some amount of online searches and finding a relevant code snippet and then fine tuning. In each of these three cases, uh, the common thread is that you have to find the right snippet. For that, you have to look somewhere, or maybe you already know the solution, and fine tuning it to that specific use case, right? This is where I think general search engines fail to solve code specific searches, and we need fine tuned solutions which can solve this problem. What's the approach that I'm proposing? uh, Different organizations have different needs, right? Their code bases have evolved over time. They have certain coding standards, guidelines, practices that they use. So code search engines also need to capture these aspects. uh, how is that? Let's consider a scenario where you want to search. We'll continue with the same example of caching an endpoint. Taking this example closer to home, I'm going to show you what we do internally at Graminer, where I work. We use Gitlab to uh, host the code, manage the source code versioning, use the CI/CD for deployment and integration. For this specific purpose, I'm going to demonstrate how this search works in GitLab and see what is lacking there. Okay. So this is where I am, code.gram.com. This is where your server is. My username is Bhanu.k, and let's say I search for cache. You will notice that you won't find any specific results because it expects you to be in a specific project. Let's say I search for a project called Grammar Charts. There's something I worked on, and you'll start noticing some results, right? You'll see some cache appears in git ignore files, markdown files. But I'm specifically interested in, let's say, markdown, sorry, YAML files or Python files. YAML is where you see the results from. So I know, okay, this file is probably I'm interested in. But this experience is naturally unintuitive because the moment you type, you expect to see some results. What I'm going to demonstrate is actually explain how the proposed solution is. Before that, I'll show you the proposed solution. This is the deployed version. Let's say you search for cache, right? And it's going to fetch you results from different projects that are indexed, right? You see each project here is IDP, process monitor, dynamics charts. Each are pre-indexed. I'll show you how this indexing is done. So this is where we expect developers to use the code search engine to find snippets relatively quickly and copy paste them and bring it to their own editor, right? You can also search for, let's say, other instances, not for cache. Maybe you want to search for Google Auth or membership, depending on how the YAML keys are, right? So this is going to be the end output. So the approach is that we're going to download the code bases for different projects, because that's what those are our gold standard for this approach, right? So you download the code, index it basically using TF-IDF, term frequency and inverse document frequency. Store that and hit an API whenever you search, right? Whenever you, as I showed you earlier, you could type, let's say, cache, membership, or log, and it hits an endpoint, which is where we serve a pickle file. Search it against that, and then find the relevant queries and get back the results. All of the work is available at github.com, Kamapantula, discover-workshop. For this purpose of the talk, I'm going to use three files. One is a process Python my modules IPython notebook, search YAML IPython notebook, and a Python utilities file. In the search YAML IPython notebook, what I'm going to show you is use an existing index that we have already pre-indexed or pre-created, and then hit the query against it, right? In the case of process Python modules, what I'm going to show you is how do you create that index, which is specific to Python files. Because the way you create indexes is what is critical to the code discovery aspect. So, at an overview, how does this approach work? Before that, I need to show you how the YAML file is actually structured. Right? I have a couple of files here. Let's say open gamex.yaml file. Hope it's visible. So I have different sections here: import, log, schedule, test, and URL. For this specific purpose, we're going to use the URL section. The moment I type for cache, I'm going to get these results, right? This specific YAML endpoint. This endpoint is nothing but, you can imagine this as roots, right? Whenever you type, let's say, slash edit, I'm going to serve this file, edit.html. It has a Google authentication against it. For this specific one, if you're going to serve static files, let's say image for the landing page, saying slash some pattern.png, I'm going to use this specific one. For the cache, for this specific purpose, you have two types of cache. One is caching at the server level. The other one is caching at the browser level. So when we type cache, we expect this handler to pop out, right? So let's see how that part is done. This is implemented in this search YAML.ipython notebook. So let's open that. Just give it a brief moment before it loads. Okay, let's reload. Yeah. So I import the necessary modules, which are from the SciPy Sparse module. I load the specific module and JSON to just load the project keys path. So in order to use the index, we first need to have the pickle file, the relevant matrix file, and the project keys file to actually look up which specific project the keyword is matching with. This vectorizer is nothing but a TF-IDF vector on top of the corpus, which is nothing but the input code. I'll show you how to structure that code. The way it works is let's say for the question cache, which is what we've typed in the URL earlier, we have to create a question vector first, which is nothing but you fit this question for the given saved vectorizer, right? Once you do that, you'll have to compare this against the existing matrix using cosine similarity. If you're not familiar with cosine similarity, no worries. I'll just show you briefly how that's done. Let's say for two different vectors, you're going to calculate the cosine similarity as the dot product between them. So 5 times 2 plus 0 times 5 plus 2 times 0. It comes to 5 times 2, which is 10. So if you look at the document part of it, let's say in our case, documents are going to be the YAML patterns, or rather the YAML code, and each column here is going to be the individual string, which is part of the larger YAML file. uh, in this specific example, the cosine similarity is going to be the sum of all the products. This times this times this times this times this. The summation of all of them, which is something like 0.26, right? So that's the cosine similarity aspect. If you want to briefly look at the TF-IDF vectorizer, we are using scikit-learn for this. This TF-IDF vectorizer is nothing but a collection of raw documents of a matrix of TF-IDF features. So TF-IDF is going to be calculated for every single word which is in your column in every single document which is into your row. So you'll have a humongous list of, humongous matrix of rows and columns. Right. Um, Now that's out of the way. Let's see. We notice that the question vector itself is 1 by 744. 744 is the number of words you have, and this is only one because you are only looking for the word cache, which is your row. The moment we calculate the cosine similarity, it's going to look up against the existing matrix, which has 1, 2, 3, 4, 5, 6, 7, 7 documents, and it's going to give you cosine similarity values against each of this. So the maximum of which is 0.1 and is 0th index. This kind of matches this project cluster slash grammars.yaml. Uh, this grammars.yaml is going to have the same structure that I showed you earlier in this grammars.yaml file, but from a different project. Right now, I'm showing you here grammar charts, but this is a perfect match for cluster project. What we're going to do next is for the URL keys inside the YAML file. URL keys meaning all the dictionary keys is nothing but dictionary, a key value pair. This is a key, and this is the whole. This whole thing is a value, right? Keys of zero is nothing but that specific project cluster.grammars cluster slash grammars.yaml, and we're going to save that all those values, right? And the moment you look for this specific match, you're going to do a we're going to pick this specific project and rebuild the index so that this time the index will only have the documents from this specific file. Earlier, what we did was, the original matrix here will have the whole YAML file as one document, and so on for different YAML files. But the moment you have a hit, what you're going to do is break that down further, because we have to identify which specific block the code is coming from, right? Which is where we do the next level of indexing. So these are the individual YAML components, and when you unravel it, when you just ravel it and calculate the maximum of it, which is to see where the match is, you'll get the indices 654 is 1, 2, 3, 4, 5, 6, right? So 7, 6 will be from 0 to 6, which is the seventh item. So the matches are 6, 5, 4, just 7, 5, and 4. So you'll have this match, and this match. And you'll notice that each of this will have a cache keyword in it. These are the matches. So what you see here are the in, are better indented for the purpose of UI experience. This is essentially the same code that you see in the IPython notebook and served here over an endpoint, right? You do the same for different examples, right? Let's say we look for the keyword form handler, and this will again look up the first level of search is against the parent YAML files. The next level of search is you look at the individual YAML components, and here you get the index 2012, which will again be part of that file. Keys of 6 would be yeah, would be the seventh item in this project case.json. So this is how you would search the YAML file. But how would you create an index, right? For the purpose of demonstrating the index creation, I'll show you how it's done in Python. It's a similar approach in YAML. We'll go back and look at the Python process modules file. Just give it a moment to load. This uses an independent an intermediate file pyutils.py. I'll show you how the utilities are structured here. In the case of Python, what we want to be able to do is to find the right function. We need to be able to index the function by itself, right? So for that, we need to identify for every function what its name, its function name, what is its doc string, and what are the different functions that are called within that function and different methods that are called in the function. So let's get going. I'll I'll just load the libraries PyUtils and OS. PyUtils is nothing but my own custom script. It has a bunch of utilities to identify the camel case for a given string. Let's say your doc string may have doc string with let's say S caps as a single word. Then this will break that into doc and string as separate tokens. Same for snake case. And we have different utilities to identify and process the doc string, its name, functions, and so on. So I'll show you whenever we come across that. For this specific thing to work, we need to be able to identify a single Python file or maybe multiple ones. Let's start with a single one for a given repository. In this case, we are using scrape.py, which is part of the Discover library. You we, we first identify the path, then we load the module. What does loading module do? You go to pyutils and look for load module. uh, Whenever your session is ongoing, when you do a load module, whatever code that you have in that specific file, escape.py, is going to get executed and be available for you to access it, right? So the moment you do that, you have it saved under discover mod. With this done, we want to identify the all the functions in that specific file. For every function, then name, docstring, method calls, and function calls. So let's find out all the functions. You do it by script is an old file. Please ignore. You can just say pyutils.file find functions of discover mod. What that will do is look for the method, the function find functions, and it will just iterate through different functions and list it out here. So you have all these functions in the specific Python file, which is script.py. Then for every function, we need to identify these properties: name, docstring, function calls, and method calls, right? Because these will become our search arguments. Whenever you search for a keyword, it's a cache, and if cache matches any of these attributes, name, docstring, function, method calls, it's going to serve as a hit for our keyword. The moment you do that, for every function, you it's the same call that we have done here. we need to be able to annotate it. Annotate is nothing but it's another method. I mean, sorry, another function which has a dictionary of the dot name functions and method calls, and these internally will call other functions in the file. So you do that, you will find that for this specific func calls, this is your whole doc string. This is its name, its functions, and the method calls. You do the same for all the functions here. And once you are done with it, this is only listing the method calls. So let's ignore that. Once we do that, we need to get to a point where we have a document matrix which is rows by columns. Here every row will be related to a function. So we use a name, docstring, method calls, function calls to create a singular string for a given function. So this whole thing will represent the first function in our list of functions. Notice that this is just string concatenated by a space. If you have any camel cases, snake cases, they would have been converted and so on. Now the way to create an index is you take this whole document's corpus and create a vectorize out of it, and create a matrix out of it. So what TF-ID of vectorize it takes is basically you give it a corpus and will create a TF-ID of feature vector for out of that. So this is where we actually began with in the case of YAML, right? When we were using the search YAML IPython notebook, that's where we actually had. That's where we actually started with. So we use the question lowercase. If I'm going to search for the lowercase, I expect camel case, snake case, and these to come up because this string lower exists in these functions, right? So you create a vector out of it and calculate the cosine similarity against that, right? So you'll notice that this specific keyword lowercase matches in so many functions, one, two, three, four, five. At least five of the functions have matches with the lowercase. The maximum of which is with the 12th index. So we can just look through uh, and see what is it that at the 12th index that'll give us the right function. These are some more examples, right? For annotate, camel, class, and glob. Look at glob. This is being used in find modules. This is what the result you get for this specific keyword. So this approach is powerful because you will only need to search for the files that you need, and not all the other files like gitignores, markdown files, and so on. So depending on what you want to search and what you're interested in, you can fine tune this approach, right? So what are the next steps from here? The moment you have the search index, the next step would be to make it more user friendly, because you just don't want to get an index, right? You want to be able to serve it against some endpoint. In our case, we are using something called Gramix. Gramix is a data science platform which is built on top of Tornado Web Framework. So that is not going to be covered in this specific talk. I leave the documentation with you. You can go to lambda.com/guide. That's where you'll find Gramix. You can find ways to install it and use it. At its core, what it is? It's a web server, web and data server with some handy utilities for uh, for data related problems. So in our case, the way we are going to use this is the moment you have a hand, the moment you have a file that you want to serve against, or maybe fetch the files, you can use something called form handlers, which will let you access data Give it a moment to load. Okay, these are again part of the grammars.yaml file. So if you hit slash flags, it will hit this flags.csv and fetch you that entire file. You can have again filters on top of it. Uh, so you want to limit it or write SQL queries against it, and so on. SQL queries only for the database related URLs. So this is what we use to serve our endpoint over here. So when you do a queue equal to membership, it's going to go to the backend, hit the index that we already have saved, and and fetch the results. Right now, you will see that this is indexed on 7 projects. We can index it on more projects. Uh, these are the projects that we have indexed these on. Right. I hope you like the talk. If you have any questions, please to raise. And you can find the material here. Please do give it a try at grammar.com/discover. And you can find me, you can email me at, say, Pantala@grammar.com, or you can find me on Twitter at Thoughtistep. All right. I hope you like the talk. Uh, Thank you for your time.